And finally, how do we actually describe sampling distribution? So the fact that statistics for random samples have definite sampling distributions allows us to answer this question: how trustworthy is a statistic as an estimator of the parameter? To answer that question, guess what we get to do? We get to consider their center, their spread, and their shape. So we get to use our little acronym and we get to cuss it out. But even though we've cussed in the past and we've talked about center, unusual, spread, and shape, we always talk about center, unusual, spread, and shape. It is as unique to its concept as possible. So unfortunately, with sampling distributions, we have some uniqueness. So I went backwards. Our center is actually going to be described as biased or unbiased estimator. So an unbiased estimator, this definition is going to pop up in just a second, but I'm going to start you with it. Is a statistic used to estimate a parameter is an unbiased estimator if the mean of its sampling distribution, so X bar, must be equal to the value of the parameter being estimated. So let's say I want to talk about the median, then my median should be equivalent to X bar, the mean of the sampling distribution, not X bar. That would be the mean of an individual sample. So the mean of the sampling distribution itself should be equivalent to any of the estimators we are using, either median or a sample's mean, et cetera, et cetera, et cetera. So in the CHIPS example, an example we will be doing in class, so in the CHIPS example, we collected many samples of size 20 and calculated the sample proportion of our red chips. How well does the sample proportion estimate the true proportion of red chips? And if you were absent for this day in class, this activity can be found on page 426, and it's used throughout this chapter 7.1. So please do get a chance to read through that or ask your classmates about that activity. So how well does the sample proportion estimate the true proportion of red chips? And just remember, we purposely created a sample set with a probability of 50% being red to begin with. The rest were just a grab bag. So let's look at that p-value distribution. So this p-hat represents the number of red chips in all of your individual sample sizes. This is obviously created using one of their Fathom softwares, but note that all the centers of the approximate sampling distribution is close to 0.5. Isn't that what it was supposed to be? It was supposed to be an estimate of 50% red. In fact, if we took all possible sample sizes of 20 and found the mean of those sample proportions, we'd get exactly 0.5. However, it would take an infinite amount of time or a very long amount of time to actually take every possible sample size of 20. If you simply look at the just general combination of values, that's a huge number of samples that you are doing. So it is a little bit difficult for us to do every single possible sample size. But if we did a huge amount, numerous, 500, 5,000, we're going to start to see that pattern exist of that 0.5. So again, here's the formal definition of an unbiased estimator. So important that you recognize to use an unbiased estimator, the mean of the sampling distribution must be equal to the true value of the parameter being estimated. Okay, spread. So we've talked about center. We're not going to talk about unusuals, but we are going to talk about our spread. Low variability is best. To get a trustworthy estimator of an unknown population parameter, start by using a statistic that is already an unbiased estimator. Median, already pretty unbiased. This ensures that you won't tend to overestimate or underestimate. Unfortunately, using an unbiased estimator does not guarantee that your statistic will be the actual parameter value, and I want to note this right here. Larger samples have a clear advantage over small. They are more likely to produce an estimate close to the true value of the parameter. However, taking a large sample does not fix bias. Remember that even large voluntary response samples or convenience samples are worthless because of bias. So small, large, it doesn't matter. Low variability will be better, but it does not mean that your bias has been removed. So please do not forget that. Don't get those two concepts confused. And finally, let's talk about just the variability. So we've talked about center, we've talked about spread. We could talk about our shape, but that's, they're going to tend to be symmetric. But you could, look at it and say it's right skewed, left skewed. But there are general rules when we're talking about the spread because we talk about variability of a statistic. So you can read through this formal definition. We talk about it as the spread, but there is a 10 times larger rule, and let's go in. It's now your opportunity to answer a question. So if this information didn't give you enough, I'll give you a preview. You are going to be talking about, you're going to use an unbiased estimator. You're going to figure out what would have happened if you had taken samples of size 20 instead of size 10. And then finally, you're going to describe the shape. And so you're going to understand kind of spread, center, and shape all in this one question. I really suggest that you attempt it to the best of your ability without looking for the solution.